Section: Introduction. In this section, we were introduced to the evolution of computer vision from its early focus on interpreting images as representations of 3D scenes to the current emphasis on processing 2D patterns. Initially, researchers delved into tasks like understanding optical properties, 3D primitives, geometric reasoning, instance recognition, affordance, and forensics. However, in the era of large language models, LLMs, the community has shifted towards tasks expressed in natural language, highlighting the vision-language connection learned by multimodal LLMs. We recognized a gap in evaluating multimodal LLMs, where existing benchmarks tend to blend perception with language knowledge and reasoning. For instance, popular benchmarks like MMBench pose questions that rely heavily on language rather than visual understanding. This conflation leads to a reductionist evaluation of perception as a dense captioning task, favoring language-based solutions over genuine visual comprehension. To address this issue, we introduced Blink, a framework that reimagines traditional computer vision challenges in a format that enables the evaluation of multimodal LLMs. Blink comprises 14 classic computer vision tasks, spanning from low-level pattern matching to high-level visual understanding. These tasks are carefully designed to require genuine image perception for accurate answers, moving away from relying solely on dense captioning. Blink consists of 3.8K questions across 7.3K images, covering a diverse range of indoor and outdoor scenes. Questions are either derived from datasets or manually crafted, presented in a question-answering format with answer choices of images or text. Despite being easily solvable by humans, these tasks prove to be extremely challenging for existing machinery, with even advanced models like GPT-4v struggling to achieve human-level accuracy. Our experiments revealed that specialist vision models outperform multimodal LLMs significantly in various tasks, indicating that the perceptual capabilities of multimodal LLMs may have been overestimated. Integrating insights from specialized models could enhance the performance of multimodal LLMs in visual tasks. Blink serves as a valuable testbed for bridging the gap between traditional perception concepts and the generative abilities of multimodal LLMs. Section Summary. In this section, we explore the evolution of computer vision from interpreting 3D scenes to the current emphasis on vision-language tasks using large language models, LLMs. We introduce Blink, a framework that reimagines traditional computer vision problems to evaluate multimodal LLMs, highlighting the gap between human perceptual abilities and those of existing machinery. Our experiments reveal that specialist vision models outperform multimodal LLMs on various visual tasks, suggesting the need to integrate insights from specialized models to enhance the perceptual capabilities of multimodal LLMs. Section: Multimodal Benchmarks. In this section, we will discuss various multimodal benchmarks used to evaluate the capabilities of models that combine vision and language. Traditional datasets focus on single tasks like optical character recognition, image captioning, and visual question answering, but they may not fully assess the overall perception and reasoning abilities of multimodal models. Recent benchmarks like MVET, MMBench, and SeedBench aim to provide more comprehensive evaluations by including a wider range of tasks. These benchmarks cover topics such as object recognition, OCR, and math, but they mainly focus on recognition-based questions. On the other hand, there are benchmarks like MMMU, HallusionBench, and MathVista that have specific focuses such as expert-level artificial general intelligence, language hallucination, and mathematical domain visual questions. However, these benchmarks do not require human-level perception abilities like Blink does. Our goal with Blink is to evaluate the visual perception abilities of existing multimodal models. We want to understand the gap between human and machine perception and explore ways to improve machine perception. Existing benchmarks mainly assess visual recognition abilities, so we introduce Blink to evaluate nuanced perception capabilities across various dimensions. Blink includes 14 tasks that require a deep understanding of visual data, ranging from low-level pattern matching to high-level visual understanding. These tasks cover different levels of complexity and scales, allowing us to systematically assess multimodal models' capabilities. To evaluate multimodal models, we convert all tasks into multiple-choice question answering problems. The questions can include single or multiple images, and the answers may be images or texts. We have curated 3.9K questions and 7.3K images for Blink, evenly distributed between validation and test sets. Blink differs from previous benchmarks in several ways. 1. Visual prompting. Blink provides visual prompts in addition to text prompts, allowing researchers to focus on specific areas within images for evaluation. 2. Perception beyond recognition. Blink evaluates a diverse set of visual perception abilities beyond recognition, such as 3D reasoning and geometric understanding. 3. Visual common sense. Blink's questions are designed to be easily solvable without domain-specific knowledge, highlighting the gap between human and machine perception. 4. Interleaved image text formats. Blink presents questions and choices in both text and image formats, challenging multimodal models' interpretive capabilities. 5. Diverse image sources. Blink includes a wide range of images from various sources to comprehensively assess visual perception abilities. These unique features of Blink set it apart from existing benchmarks and provide a more thorough evaluation of multimodal models' visual perception capabilities. Section Summary. Multimodal benchmarks. In this section, we introduce various multimodal benchmarks designed to evaluate the capabilities of language and vision models. These benchmarks cover a wide range of tasks, from recognition-focused questions to more nuanced perception abilities, such as 3D reasoning and geometric understanding. The Blink benchmark stands out by focusing on visual perception beyond recognition, offering diverse tasks that do not require domain-specific knowledge and incorporating a mix of text and image formats to push the interpretive boundaries of multimodal models. Section: Dataset Collection Process. In this section, we present the process of collecting the dataset for Blink. Blink consists of 14 tasks that have been transformed into multiple-choice question-answering formats. These tasks use a wide range of images from different sources, ensuring that each test sample contains unique images. One of the tasks, called Visual Correspondence, assesses multimodal ILM's ability to recognize the same point in a scene across different viewpoints, lighting conditions, or times. We use H-patches for this task, which contains image sequences taken under various illuminations and viewpoints. Another task, Relative Reflectance, involves comparing the reflectance of two pixels to evaluate the model's understanding of material properties and their interaction with light. Human annotations from the intrinsic images in the wild IIW dataset are used to curate samples for this task. The Relative Depth task evaluates the model's capability to judge relative depth, with samples curated from human annotations in the depth in the wild dataset. Spatial Relation task focuses on understanding spatial relationships between objects in a scene, which is crucial for interpreting visual environments. Samples for this task are curated from the Visual Spatial Reasoning dataset. Multi-View Reasoning task evaluates the model's ability to deduce relative camera motion based on images of an object from different viewpoints, using data from the wild 6D dataset. Jigsaw task assesses the model's capacity to recognize and group patterns based on shape, color, and texture continuity in images from the Terra dataset. Art Style task evaluates the model's capability to analyze and distinguish art styles among images, using paintings and stylistic information. Object Localization task tests the model's accuracy in detecting and localizing objects in images from the LVIS dataset. Counting task evaluates the model's abilities in detection, recognition, and compositional reasoning in complex scenes using questions from the Tally QA dataset. Forensic Detection task assesses the model's capability to distinguish between real and synthesized images. IQ Test task evaluates the model's graphical reasoning abilities without requiring domain-specific knowledge. Visual similarity task aims to determine if the models understand visual features, patterns, and aesthetics comparable to humans using samples from the DreamSim dataset. Semantic correspondence task focuses on matching semantically similar elements across images using samples from the SPAIR71K dataset. Functional correspondence task challenges the models to identify functionally similar points across objects using samples from the FUN-K-point dataset. To ensure the quality of BLINK, we manually review all collected data to filter out any ambiguous or low-quality data. Section Summary. In this section, we detail the dataset collection process for Blink, which encompasses 14 tasks transformed into multiple-choice question-answering formats. Tasks like visual correspondence, relative reflectance, and relative depth evaluate multimodal ILM's abilities in understanding scenes, material properties, and depth perception. By curating samples from various datasets and refining tasks like spatial relation and object localization, we aim to assess the model's spatial reasoning and object detection capabilities accurately. Section: Experiments. In this section, we describe the experimental setup and the baselines. We evaluate 16 recent multimodal LLMs and find that Blink poses a challenge for existing models. We also conduct detailed analyses on various experimental settings, such as reducing images to captions, different visual prompts, and error analysis. For the experimental setup, we assess Blink on different multimodal LLMs, including models like MINI GPT-4 v2, OpenFlamingo v2, and others. We use standard evaluation setups and do not resize images during experiments. We extract choices from model outputs using predefined rules and GPT 3.5 Turbo. In terms of main results, we observe that the performance of open-source multimodal LLMs ranges from 35% to 42% accuracy, which is close to random guessing. The best model, LLAVAV 1.6 to 34B, achieves 45.05% accuracy. Even the most advanced models like GPT-4 Volts and Gemini Pro have accuracies around 51%. However, they still lag behind human performance significantly. Multimodal LLMs excel in tasks like spatial reasoning, art style, and counting, where they outperform random guessing. They also show strengths in relative depth and forensics detection. However, they struggle with tasks requiring pixel-level and crop-level understanding. We conduct experiments to see if dense image captions alone can suffice for multimodal LLM benchmarks. Surprisingly, we find that using captions along with text-only models can outperform some multimodal models in certain tasks. Visual prompting also plays a significant role in the performance of multimodal LLMs. Specialist models outperform multimodal LLMs in certain tasks, indicating potential for improvement in multimodal models with the right data and training strategies. Error analysis of GPT-4v reveals common types of errors, such as hallucinating fine-grained patterns and misinterpreting visual prompt locations.